Today's topic is Maxwell's thermodynamic relations. We have four thermodynamic energy functions or thermodynamic potentials that are U, F, H and G. U is internal energy, F is Helmholtz free energy, H is enthalpy and G is Gibbs potential. These are the four thermodynamic energy functions or thermodynamic potentials. These are functions of thermodynamic variables P, V, T and S. And from these four thermodynamic potentials, we find four Maxwell's thermodynamic relations. Now we consider the first thermodynamic potential, that is internal energy U. According to kinetic theory, each matter is made of molecules. There are two types of energies of molecules. One is potential energy, which is due to intermolecular attraction forces between the molecules. And second is kinetic energy, which is due to motion of molecules. And sum of total potential energy and total kinetic energy of all the molecules of a system is known as internal energy of that system. So internal energy U of a given system is equal to sum of kinetic energy plus potential energy. Kinetic energy is due to motion of molecules and potential energy is due to intermolecular attraction forces between the molecules. From first law of thermodynamics, heat given to a system dQ is equal to sum of change in internal energy dU and work done by the system dW. That is dQ equal to dU plus dW. So this is the first law of thermodynamics. Heat given to a system dQ is equal to dU plus dW. dU is change in its internal energy and dW is work done by the system. And work done by the system dW is equal to PdV. So we can write it as dQ equal to dU plus PdV. We write it as equation 1. And from second law of thermodynamics, if the system absorb heat dQ at absolute temperature T, change in entropy of the system is given by ds equal to dQ upon T. This is the definition of entropy. Change in entropy, ds is equal to dQ upon T. dQ is the heat absorbed by the system at temperature T. Then from this equation we can write dQ equal to Tds. This is the mathematical form of second law of thermodynamics. We write it as equation 2. So we have these two equations. One from first law of thermodynamics, that is dQ equal to du plus dW, which is equal to du plus pdV, and second is from second law of thermodynamics, dQ equal to Tds. Now substitute this value of dQ, which is equal to Tds, in this equation 1. We get Tds equal to du plus pdV, and this gives the value of du, change in internal energy, and this du is equal to T ds minus P dv. We write it as equation 3. So this is the expression for du, change in internal energy, in terms of 4 thermodynamic variables T, S, P and V. Internal energy U is a point function, so du is perfect differential. Now we find Maxwell's first thermodynamic relation from this equation 3 for change in internal energy du. To find the Maxwell's thermodynamic relation from this equation, we first look at the right hand side. There are two terms in the right hand side. First is T ds and second is P dv. If we keep V constant, then dv becomes 0 and second term will become 0. And if we keep S constant, then ds will be 0 and first term will become 0. So we find the partial differentiation of u with respect to S by keeping V constant, and again we find partial differentiation of u with respect to V by keeping S constant. There are two terms in right hand side. The differential terms are ds and dv. So we find partial differentiation once with respect to S keeping V constant, and then partial differentiation with respect to V by keeping S constant. So if V is kept constant, second term is 0, dv is 0, so P dv is 0, then du equal to T ds. This gives delta u upon delta s equal to T, and we get this equation delta u upon delta s equal to T, and this is for constant V. So we write in left hand side delta u upon delta s at constant V equal to T. Draw a line in front of delta u upon delta s and put V below it. This V means that it is for constant V, for constant volume. Similarly, if we keep S constant, then first term will become 0, and then we have du equal to minus P dv. Then delta u upon delta V will be equal to minus P. So we write this second equation delta u upon delta V equal to minus P, and it is for constant S. So we find these two equations 4 and 5. Delta u upon delta S at constant V equal to T, and delta u upon delta V at constant S equal to minus P. First one is partial differentiation with respect to S, V is constant, and in second we have partial differentiation with respect to V and S is constant. Now we find the partial differentiation of these two equations 4 and 5. We differentiate partially these two equations, first now with respect to V and second with respect to S. In equation 4, this is the partial differentiation of u with respect to S. Now we differentiate it with respect to V. And the fifth equation, which is partial differentiation with respect to V, now we find its differentiation with respect to S. So from equation 4, if we find partial differentiation of this equation 4 with respect to V, Put delta upon delta V before left hand side and right hand side. So we get this relation delta upon delta V, delta U upon delta S equal to delta T upon delta V. And this is the differentiation with respect to V. So we write for constant S in left hand side and in right hand side. Similarly, if we find partial differentiation of this equation 5 with respect to S, put delta upon delta S before left hand side and right hand side, then we get this relation delta upon delta S, delta U upon delta V equal to minus delta P upon delta S. Put delta upon delta S before left hand side and right hand side of this equation 5, we get this relation, and it is for constant V. So we write at constant V in left hand side and in right hand side also. Now we see that these are equations 6 and equation 7. In these equations 6 and 7, the left hand side is 2 times differentiation of U. In this relation equation 6, we have this 2 times differentiation of U. It is first with respect to S and second with respect to V. And in equation 7, in left hand side, we also have 2 times differentiation of U. Now first with respect to V and second with respect to S. Since du is perfect differential, so the left hand side of these two equations 6 and 7 will be same. So right hand side of these two equations will also be same. So put the right hand side of these two equations 6 and 7 equal, and we get the relation delta T upon delta V S equal to minus delta P upon delta S V. This is the Maxwell's first thermodynamic relation. Delta T upon delta V at constant S equal to minus delta P upon delta S at constant V. Second Maxwell's thermodynamic relation can be obtained by this thermodynamic potential, which is Helmholtz free energy. Helmholtz free energy or Helmholtz function, we write it by capital F, and it is defined as F equal to U minus Ts. Differentiating this equation 9, F equal to U minus Ts, we get dF, which is equal to d of U minus Ts. It is differentiation of U minus Ts. So this is equal to du, differentiation of U, and then we have minus differentiation of Ts, and differentiation of Ts is t ds plus s dt. First function differentiation of second plus second function differentiation of first. So we get df equal to du minus tds minus s dt. And now put the value of du, which we obtained earlier. We obtained value of du from equation 3. It is equal to tds minus ptv. So put the value of du, which is equal to tds minus pdv. Put this value here. For du, we write tds minus pdv. Other terms are minus tds minus s dt. The two terms are cancelled out, tds and minus tds. Remaining terms are minus pdv minus s dt. So now this is df. df equal to minus pdv minus s dt. F is also a point function, so df is perfect differential. And now we can find out Maxwell's second thermodynamic relation from this equation dF equal to minus P dV minus S dt. In a similar manner as we find the first thermodynamic relation. Here in right hand side there are two terms, minus P dV and minus S dt. If t is kept constant, then second term becomes 0, dt becomes 0, so second term will be 0. And then dF will be equal to minus P dV. If we differentiate partially with respect to V, then we get delta F upon delta V equal to minus P. It is for constant t when second term is 0. So we get this relation delta F upon delta V equal to minus P. It is for constant t. And similarly, if we keep V constant, then first term will become 0 and then dF will be equal to minus S dt. So delta F upon delta t will be equal to minus S, and we get this relation delta F upon delta t equal to minus S. It is for constant V. These are equations 11 and 12. In 11 we have partial differentiation of F with respect to V, t is constant, and in 12 we have differentiation of F with respect to t and now V is constant. Now we again differentiate these equations 11 and 12. Partial differentiation of 11 is now with respect to t by keeping V constant, and partial differentiation of this equation 12 we now have with respect to V keeping t constant. So we find if we make partial differentiation of 11 with respect to t, put delta upon delta t before left hand side and right hand side, and we get this relation, and it is for constant V. So we write constant V in left hand side and in right hand side also. So we get this relation 13. Similarly, if we find partial differentiation of this equation 12, now we partially differentiate this 12 with respect to V, keeping t constant. So we put delta upon delta V before left hand side and right hand side and get this relation delta upon delta V, delta F upon delta t equal to minus delta S upon delta V, and it is for constant t. So we write constant t in front of left hand side and right hand side. Now these are equations 13 and 14, and in these two equations the left hand side will be the same because dF is perfect differential. So left hand side of these two equations 13 and 14 will be same, that is delta upon delta t delta F upon delta V is equal to delta upon delta V delta F upon delta t. So right hand side will also be the same. This is the right hand side of equation 13. It will be equal to this right hand side of equation 14, and this gives the Maxwell's second thermodynamic relation, which is delta P upon delta T at constant V equal to delta S upon delta V at constant T. Maxwell's third thermodynamic relation is obtained from thermodynamic potential, that is enthalpy H. Enthalpy H of a system is defined as sum of energy of system U and work energy PV. Enthalpy H is defined as equal to U plus PV. U is internal energy of the system and PV is known as work energy. Since work done dW is PdV, so we write PV as work energy. So enthalpy represents total energy of the system, internal energy plus work energy, U plus PV. If we differentiate this, then we get dH equal to du plus pdv plus vdp. Differentiation of PV is pdv plus vdp. First function differentiation of second plus second function differentiation of first. Now put the value of du from equation 3 as we have done earlier. This is du equal to tds minus pdv. It is from equation 3. Remaining terms are pdv plus vdp. Again two terms are cancelled out, that are minus pdv and plus pdv, and we get dh equal to tds plus vdp. dh is h is also a point function, so dh is also perfect differential. And we can find Maxwell's third relation from this equation, that is equation 17, dH equal to TdS plus Vdp. We can find the Maxwell's thermodynamic relation, third relation, from this equation, that is 17, in a similar manner as we find Maxwell's first and second relations. Now, if we keep S constant, then first term of right hand side becomes 0, ds becomes 0 if S is constant, and if we keep P constant, then dP is 0, the second term will be 0. So if we keep P constant, then second term will be 0 and we have dH equal to TdS, or delta H upon delta S equal to T. This is this relation 18, delta H upon delta S is equal to T, and it is for constant P. And similarly, if we keep S constant, then first term will be 0, and then we have dH equal to Vdp, or delta H upon delta P equal to V. It is for constant S. So we write this equation delta H upon delta P equal to V. It is for constant S. So we write these two equations 18 and 19. Now we partial differentiate this equation 18 now with respect to P, keeping S constant, and similarly we differentiate partially this equation 19 now with respect to S, keeping P constant, and get these two equations. If we find partial differentiation of 18 now with respect to P, put delta upon delta P before left hand side and right hand side, and we get this equation, that we write equation 20. Similarly, if we differentiate partially equation 19 now with respect to S, keeping P constant, then we put delta upon delta S before left hand side and right hand side of 19, and P is constant, then we get this relation 21. Now dH is perfect differential, so left hand side of this equation 20, which is this, will be equal to left hand side of this equation 21, which is this, that is delta upon delta P, delta H upon delta S equal to delta upon delta S, delta H upon delta P. Left hand side of these two equations 20 and 21 are same, so right hand side will also be same, that is delta T upon delta P at constant S will be equal to delta V upon delta S at constant P, and this gives the Maxwell's third thermodynamic relation. Delta T upon delta P at constant S is equal to delta V upon delta S at constant P. Maxwell's fourth thermodynamic relation is obtained by Gibbs potential G. Gibbs potential G is defined as G equal to U plus PV minus Ts. U plus PV is enthalpy and U minus Ts is Helmholtz free energy, and U plus PV minus Ts is Gibbs potential. Differentiating this equation, we get dG equal to du plus pdv plus vdp. Correct it. It is not pdp. pdv plus vdp, then minus tds minus sdt. Now 4 terms will be cancelled out. Here we put also the value of du from equation 3. From equation 3 put the value of du, that is tds minus pdv, and we have these terms. Out of these terms we cancel out 4 terms and remaining terms will be these two, v dp minus s dt. dg equal to v dp minus s dt. This we write as equation 24. G, Gibbs potential G, is also a point function, so dg is also a perfect differential. We now find Maxwell's fourth thermodynamic relation from this equation. If we keep in right hand side, we see there are 2 terms, v dp and minus s dt. If we keep p constant, then dp is 0, first term will be 0, and if we keep t constant, then dt is 0, second term is 0. So if we keep t constant, second term is 0, then dg equal to v dp or delta g upon delta p equal to v. So we have this equation, delta g upon delta p equal to v. It is for constant t. And similarly, if we keep p constant, then first term will be 0, dp is 0. Then we have dg equal to minus s dt. This gives delta g upon delta t equal to minus s. Delta g upon delta t equal to minus s. This is for constant p. So we write these equations as equation 25 and equation 26. Now make partial differentiation of this equation 25 now with respect to t, keeping p constant and get so if we find partial differentiation of equation 25 with respect to t, put delta upon delta t before left hand side and right hand side and get this relation, that is 27. If we differentiate this equation 25 with respect to t, now keep p constant. And similarly, from this equation 26, now we differentiate partially it with respect to p. So put delta upon delta p before left hand side and right hand side and get this equation 28. And if we are differentiating this equation 26 with respect to p, we find delta upon delta p of this equation. Then we keep t as constant. So we keep t constant and get this relation 28. In relation 27 and in relation 28, the left hand side of both these two equations are same because dg is perfect differential. So left hand side of 27 and this left hand side of 28 are same. Delta upon delta t, delta g upon delta p equal to delta upon delta p, delta g upon delta t. So right hand side will also be the same. This is the right hand side of 27, delta v upon delta t p, and this is the right hand side of 28 minus delta S upon delta P at constant T. These will also be the same, and we get this relation delta V upon delta T P equal to minus delta S upon delta P T. This is the Maxwell's fourth thermodynamic relation. So we find Maxwell's four thermodynamic relations. These are relations between four thermodynamic variables P, V, T and S.